Welcome to the Solutions for Math 2414 Sample Exam 2. This will be the first segment. Problem number 1. In the Larson textbook, we call this, it's called the disguised form of the log rule. Now, if you see this problem, it's not necessarily going to be titled that when you see it. Might just say, there it is, because technically an integral doesn't necessarily have to tell you how to do it. It's just helpful if it does. But this is the one you see you could not use substitution in its original form unless you had another e to the negative x on top. Then you would let u be the entire denominator. But here, this is what you have to do. This is where you have to multiply. So if it's e to the minus x on bottom, you multiply top and bottom by e to the positive x. If this was e to the positive x on bottom, you multiply top and bottom by e to the negative x. It's the opposite sign. And you should see that in my notes, I should have one example of each of those done. So it's always the opposite sign. So when you multiply every term by e to the x over e to the x, see the two ones will become e to the x. But when you multiply e to the x times e to the negative x, you actually get 1. Because basically it would just be e to the x divided by e to the x. So now you see we've transformed it into a new form where now you can let u be the entire denominator. So u equals e to the x minus 1. And then du is e to the x dx, so we don't have to make any adjustments for that. And that means du over u integral, which is a natural log. And then you have the natural log of the absolute value of e to the x minus 1 and then plus c. So that's, I'm assuming the name disguised form of the log rule is based on, in its original form, it was not a log integral, but as soon as we made that transformation by multiplying by the e to the x over e to the x, we made it into an integral that we could use the log rule for. So number 2, when you see functions like this, these trig functions, trig functions are kind of unique. Sometimes there's lots of ways you can go about solving them. But this is a technique that, for this particular problem, requires using conjugates. Now, you could convert this technically to sine and cosine. Well, there's no cosine, excuse me. And then still do conjugates. Because if you made this on the bottom be, 1 over sine, you'd get 1 over sine minus sine over sine, and you'd flip it over, and that would be sine of x over sine of x minus 1. But then you could do sine right here. Anyway, I'll just go ahead and finish it as this, done this way. So you multiply top and bottom. You'll get cosecant squared minus 1 on the bottom, which is the trig identity. That's the same thing as cotangent squared, because 1 plus cotangent squared equals cosecant squared. On the top, okay, pretty obvious, you're just multiplying by 1, so it leaves it as is. Now when you get to this step, it needs to be split up into 2 fractions. You see what I did? Here's the work right over here. Convert cosecant, cotangent squared over into sines and cosines. And you end up with sine over cosine squared. Now this would be interesting, this fraction right here, actually, if it was cotangent on the bottom and cosecant squared on top, because then you would just have du over u. Well, actually you would have negative du over u. But because the derivative of cotangent is cosecant squared. So you would actually have just u substitution. But not for this one. So if that doesn't work, then you got to figure it's convert to sines and cosines, which it is. So just do that, flip it over, and you'll get sine over cosine squared. 1 over cotangent squared is the reciprocal of tan squared. And then sine over cosine squared just becomes u substitution. That u equal cosine. Now, I didn't write it here, but when you let u equal cosine, though, the derivative will be negative sine. So yeah, you have to adjust for the derivative of the negative out on the outside. And to integrate tan squared, that's the same thing as sec squared minus 1. And so then you come down here. So then basically this one, you're integrating the negative of u to the negative 2 du. And then the antiderivative of sec squared is automatically tangent. Antiderivative of 1 is x. Now, I kind of skipped a couple steps here, but let me explain what happened. Antiderivative of u to the negative 2 would be u to the negative 1 over negative 1. That would kill the negatives. And u was cosine. So, yeah, technically 1 over cosine is correct, but if you're looking at a multiple choice answer, that would be right mathematically, but you would probably see that answer written as secant. But yeah, you get u to the negative 1, which is 1 over cosine, which actually is secant. Okay, so let's come down here. Now we're starting integration by parts. All right, whenever you have x's combined with natural log, and I might as well go ahead and throw in arc sine and the arc functions, that the u will be not the x, it'll be the log or the arc. So in this case, so that automatically makes our decision for us, which is the u and which is the dv. The u has to be the natural log. So that makes du equal x to the negative 1, 1 over x dx. I just left it as x to the negative 1. Makes it easier the next step to combine the exponents. dv is x to the 1/3, which makes v equal 3/4 x to the 4/3. So remember, it's the antiderivative, and you're going from dv to v. So basic power rule from here to here. Now, one thing that's always important when you're doing integration by parts is that make sure, I just kind of drew that. I do that a lot in my notes, but obviously you don't have to do that on a test. But make sure that your u and your dv multiplied together equals what you're actually integrating. And you see it does here, doesn't it? Is x to the 1/3 ln of x dx. So you don't have to draw that line, but you want to at least take a look at it, because obviously if that's not true, then you just kind of made up a completely different problem. You're solving something that's not even what you started with. So that would be nice sometimes in math if you could just say, hey, I'd like to change the problem. I don't like that one. I'd rather do something else. Unfortunately, it doesn't work that way. All right, parts formula, which that's on your formula sheet. I didn't put it here in the solutions, but so the integral of u dv equals uv minus integral of v du. So we have u times v right here. Remember, we don't integrate u times v, so we don't really worry about that too much. But there's uv, and then the integral of v du. That's one reason I left that as x to the negative 1, just so I could combine the exponents like this way, but it doesn't matter. You could have written 1 over x and come up with the same result. So I have 3/4 x to the negative 1, x to the 4/3 dx. Kind of skipped a step here. Well, I'll explain what I skipped. You combine those two x's together, that's going to give you x to the 1/3. So then when you do the power rule, well, here it is again, right here, x to the 1/3. So you see what that's going to be. X to the 1/3, the antiderivative of x to the 1/3 is going to be 3/4 x to the 4/3. So we have a 3/4 here. So what essentially happens is we create another 3/4 multiplied together. So 3/4 times 3/4 makes that 9/16 x to the 4/3. And then, of course, the beginning, first part, we didn't have to integrate that. We were already done. So this would be our final answer. Now, the next one, number 4, you want to use log properties whenever it's applicable. That's always helpful. And in fact, it'd be kind kind of tricky or a little extra work if you didn't use log properties here. It'd make it a lot longer. So the natural log of x squared allows me to bring that 2 down and just treat that as a constant. Now that makes u would be ln of x, dv would be x dx. So now I just kind of wrote this as 1 over x this time. So you see it didn't matter whether I write 1 over x or x to the negative 1. So dv is x dx, which makes the antiderivative 1/2 x squared. So we come down here, and don't forget the 2 here applies to everything all the way across there. You know, one thing I could have done, looking at this now, I just realized that when I brought the 2 down, I could have left the 2 with the x right over here with the dv. That would have been fine. I could have left dv as 2x dx, and then I would have had x squared there for v. But I'll just go ahead and finish the way I've done it. But the important thing is the way I did it here, though, is realizing that the 2 must be multiplied by everything in the integration by parts formula. All right, so remember uv, we just multiply those together. We don't integrate them. X squared over 2 ln of x minus, now you combine v du right here. So x squared over x would just leave me an x. Brings a 1/2 to the outside. Or you see, since both these have 2's, and there's a 2 on the outside, in this case, then the 2 would distribute through and cancel out both those 2's. Okay, so that takes care of those anyway, which obviously that would have been done if I would have did what I said earlier about letting dv be 2x dx. That would have been the same thing. And then that's just going, so the antiderivative of x dx, and of course, will be 1/2 x squared again. So our final answer would be x squared ln of x minus 1/2 x squared, and then our trusty plus c that needs to be there at the end. Number 5. Now, if you, I just did this using the tabular method, but yes, if somebody, on an exam didn't know how to use a tabular method or forgot about it, whatever the reason, you could technically do integration by parts twice. But knowing this tabular method does make things a lot more efficient and quicker. And the tabular method is best used when you combine x with either sine, cosine, or e. I mean, I possibly could do it with the ln's and the arcs, but there's no point, because the ln's and the arcs, you only have to do integration by parts once anyway. So there's no benefit to using the tabular method. The tabular method is beneficial because to simplify repeated integration by parts. I think there's an example in my notes, like I have like x to the 100 or x to the 200 power combined with ln of x. It was still one integration by parts. But if you take x to the 100 and you combine it with something like e, sine, or cosine, you have a giant mess. It would be 100 integration by part steps, which obviously, you're never going to be forced to have to do that. But so the tabular method is really of no benefit when it's logs and arc functions, inverse trig functions. But here it's nice. So you start the x, the u is still the x, just like that's the way you would choose it if you were doing it by regular parts. You differentiate that down until you get to you stop at a constant. And we have this sign chart that goes in there automatically. You start with plus, and you just keep alternating, plus, minus, till you're down to your constant. That'll be the last one. And then you have to be careful here. Then that means your cosine of x. You don't have to write the dx there, but cosine, your dv is cosine. Remember, you're integrating when you're going backwards. That's the common mistake that students often make, is they tend to take the derivative. But the antiderivative of cosine, you don't have to do this in your head. If you need to write some stuff down, you can. Antiderivative of cosine is positive sign, not derivative. Yes, the derivative of cosine is negative sign, but the antiderivative of positive cosine is positive sign, which makes the antiderivative then of positive sign will be negative cosine, and then the antiderivative of negative cosine would be negative sign. And then you always connect this pattern, like so your dv is never used in your answer, but you always connect in this pattern like that. Connect the terms in that form. You take into consideration the pluses and minus. Of course, the only time it's going to be affected is when there's a minus there. And then that's going to be the answer. And so you see you just connect them, multiplication, it'll be x squared sine x. Now you have a negative here, but then you have a negative as far as the sign chart goes. So the two negatives together make positive. So we have plus 2x cosine of x, and then minus 2 sine of x plus c. And then there you go. And that will be the answer. Same thing with this next one. You can use integration tabular method for parts here. So we go x squared, be 2x and 2. So then the sign chart goes plus minus plus. E to the 3x. Once again, we're taking the antiderivative. The antiderivative of e to the 3x will be 1/3 e to the 3x. Not 3. That's the common mistake people make. But then once you know, so it's always just going to be the antiderivative will be whatever 1 over whatever that coefficient is, plus or minus. If it was negative e to the 3x, it'd be negative 1/3 here. And the easy thing then from there on out is then you just keep multiplying by that same number. So 1/3 times 1/3 is 1/9 times another 1/3, 1 over 27. You would just keep multiplying by 1/3. And we connect in this pattern that we're supposed to for parts, tabular method for parts. So you see we have a positive, so it'll be 1/3 x squared e to the 3x. We have positive times positive here, but we had that negative from that sign chart. So it actually makes it negative right here, negative 2/9 x times e to the 3x. And then 2 over 27 e to the 3x, positive, positive, and then plus c. That would be our final answer. Now the next one, I didn't actually put the problem in here, but obviously you have the problem on the original. I guess I could have brought up the original file, but you can see by u and v, then that means that, or u and dv, that the original problem had to have been integral of x arctan of 2x dx. Because I'll let u be arctan of 2x. So we take the derivative of that, and arctan is on your formula sheet. So it's basically du over 1 plus u squared. So the derivative of 2x is 2. And 2x all squared is 4x squared. So it's 2 over 4x squared. I guess technically I should have a dx here. That's a mistake on my part. Oh, that's all right. But yeah, it should be 2x. I mean, it should be dx. And then if dv is x dx, the antiderivative would be 1/2 x squared. So now we put u and v together right here. So there's u and v, which we don't integrate, so we don't care. And v du. Now, looks like I left something out here, but let me explain what happened. Is yes, there's a 1/2 here for this x squared, but there's a 2 from here. So what I did is then you just multiply the 1/2 and the 2 and they just cancel. So that's why you don't see anything there. But I guess maybe I could have written the 2 and the 1/2 and then canceled it. But so there would have been a 2, then there would have been a 1/2, and then they would have canceled. Now we have what's called an improper integral here, meaning that we have a larger power on top. I'm sorry. Well, if the larger power is greater than or equal to the one on bottom, you have to use division. Now, it doesn't matter that that's a 4x squared and that's an x squared. The key is they're both x squareds. So you can divide a larger x squared into a smaller x squared. It just means you're going to get a fraction. So basically, x squared divided by 4x squared would be 1/4. Then you distribute, and remember, because it's division, we are subtracting here. So that's always subtraction. And the x squareds cancel. That leaves a minus 1/4. Because you're saying 0 minus 1/4. So here's your quotient. Here's your remainder over the divisor. So you have an integral of 1/4. Then you have 1/4 over 4x squared plus 1. So be careful with this negative, because it distributes all the way through. So it makes this a negative right there in front of that. Negative times negative is positive. And so the antiderivative of 1/4 would be 1/4 x. Now you come over here. So I just kind of pull the 1/4 out of the way like that. And that's arctan. So you're going to let u be 2x, du will be 2dx, and you see u squared then becomes 4x squared. So you basically have u squared plus 1 on the bottom. So that means your a is 1. But then you have the 1/4 on the outside. Now, the 1/8 comes from the fact that you have no a. Obviously there's a 1 over a as part of the formula. But you have this 1/4, but you have to adjust for the du being 2dx here. So you'd have to put a 1/2. So it's 1/4 times a 1/2 from there makes that 1 over 8. And then there's our final answer with our important plus c in there. Now we have an integral of the natural log of x squared plus 1. So that means natural log of x squared plus 1 would be your u. dv would just be dx. So the antiderivative dx will just be x for your v. And then the derivative of x, so it's a derivative of x squared plus 1, which is 2x, over x squared plus 1. So that means we have u times v, which we don't care about integrating in at all. But we do here, v du. So I have 2x over x squared plus 1 times x. Which obviously 2x times x becomes 2x squared. So we have 2x squared divided by x squared plus 1. So similar to the last problem, we also have then division because it's an improper fraction. So we divide. 2x squared divided by x squared is 2. So 2 times x squared will be 2x squared. 2 times 1 is 2. Subtract makes that a negative 2. And then we have, so we come over here, be careful with the minus again, because minus and that minus becomes plus. So you then, this integral becomes the integral of 2 minus 2 over x squared plus 1, which that's in perfect arctan form. So the antiderivative of 2 would be 2x, and then 2 over x squared plus 1 would just be 2 arctan of x. And there we go. The next one, number 9, is just arctan, no x term on this one, so but still the same idea as you let u equal arctan, 2x. So the derivative of 2x is 2 over u squared plus 1. So it'll be 2x all squared, be 4x squared plus 1. dv equals dx. And then v would be x. So UV is right here, x arc tan of 2x. And then we have b du, x times 2 over x squared plus 1. Now, that's just going to be substitution. Yeah, I guess I didn't write that out over here, but u equals, I'm not using a stylus, so this is difficult. Just using a mouse. 4x squared plus 1. du would be 8x. All right, that means we're going to have a 1/8. 8x dx. So we're going to have a 1/8 on the outside. So we have this 2 in the numerator times that 1/8 that'll be generated here, and that's where the 1/4 is coming from. Now, once again, a just happens to be a squared, happens to be 1. If a squared was something other than 1, we would have 1/4 times 1/a out here. But a is just 1. So there would have been, the fraction would have been different. So that takes care of the integration by parts.